All right. Hello, everyone, and welcome to Japan. So, today we're gonna be talking about the Nyquist plot. As we have learned, for the frequency response of a system, there can be two types of plots. The first one, which we already have discussed, is called the Bode plot, which shows both magnitude and phase, and both are functions of frequency in separate plots. Then the other type of plot that will show the frequency response is called the Nyquist diagram or Nyquist plot. And so to demonstrate what a Nyquist diagram or Nyquist plot is, we will show here an example. So let's take for transfer function g of s is equal to 1 over s plus 2. Okay. Now in frequency response, the way that we will do things is we first transform s into j omega. And now this expression of j omega must be converted. So this one needs to be converted to the x plus jy form. And we will see the reasoning behind this in a little while. And so to convert this into x plus jy form, our original function, we multiply it with its conjugate, which will give us this expression here. Okay. And so now this is now the x and jy form, where your x is 2 over 4 omega squared, and your y is negative omega over 4 plus omega squared. So both x and y are functions of the frequency. So from there, we could calculate the magnitude. Okay, so the magnitude of our transfer function in terms of its frequency response is equal to the square root of its x component squared and its y component squared. So, and then the phase angle of our transfer function is the arctangent of, okay, and so given our transfer function, the magnitude is equal to its the x component is 2 over squared plus negative omega 4 plus squared. Okay, and so we end up with this expression right here, 2 squared plus omega squared over 4 plus omega squared. So this could be simplified as the square root of 2 squared plus omega squared over 4 plus omega squared. And so our magnitude is further simplified to 1 over the square root of 4 plus omega squared. So that's the magnitude. And then the phase angle is the arctangent of the y component divided by the x component. So we have, so this is also called as the analytical expression of your frequency response. So try to practice it with 2 poles and 3 poles and a second order system to find the analytical expressions of those type of systems. So now let's go and plot this analytical expression using the Nyquist plot. The Nyquist plot could also be called as a polar plot because it is plot using the real axis as x and j omega as y, where the magnitude is expressed as the length of the phasor. So this one is your magnitude. And the phase angle is the angle of your phasor. Now remember that both magnitude and phase are functions of the frequency. And so we will then calculate the magnitude and phase for omega equals 0 to infinity. However, we will only, because that's 0 to, that's a lot of numbers, that's infinite number of points, we'll only calculate about 5 points and then estimate the shape of the frequency response. Okay. So now let's go ahead and for this expression, so we remember that the magnitude is equal to 1 over the square root of 4 plus omega squared, and the phase angle is the arctangent of negative omega over 2. Okay? And so we'll first solve for, okay, so let's make a table here. So for omega, And then we have the magnitude. Then we have the phase angle. So for frequency of 0 radians per second, okay, for 0 radians per second, okay, so let's write that there. For omega equals 0, your magnitude will be 1 over the square root of 4, which is 1/2. Okay? And your phase angle for that one, arctangent of 0 is 0. Okay? And so if we will plot this one, so let's say I will plot that. Okay, and just for the sake of, so we'll call this as our 1, 2, 3, 4, 5. So we call that as 0.5, 0.4, okay. So we could see that for omega equals or omega equals 0, it will be right here. Okay, I forgot to put in the labels. That is very important. And we'll write here 1, 2, 3, 4, 5. We'll also put that as 0.5 negative, 0.4 negative. Okay, so now let's continue, and we'll calculate for angle of infinity. We know that for angle of infinity, the angle is 90 degrees. And we also saw this in the Bode plot, like for the let me write down here. This is the phase. Remember, you have 0, 45 degrees, and 90 degrees. And for every decade, right? We have this, and then 45, and then 90. So the maximum angle for pole is, or first order system, is 90 degrees as the frequency goes to infinity. Right, so it's 90 degrees. And if we substitute infinity for our omega for our magnitude, 1 divided by infinity is 0. And so 0, 90 degrees will be right here. Okay? So this one here is for omega equals 0. This one here is your omega equals infinity. Now we'll try to fill in the tables with phase angles from different values. So we'll try we'll try 30 degrees, 45 degrees, and 60 degrees. Now, so we now have 5 points right here. Okay? So for 30 degrees, so let's write that here. The tangent of 30 degrees is equal to 0.577, which is also equal to the negative omega over 2, right? Giving us a value of omega to be 1.154. Okay, because remember that the phase angle is the arc tangent of negative omega over 2. And so if we have a phase angle of 30 degrees, and so we get the tangent 30 degrees is equal to negative omega over 2. Okay. Makes sense. Or we'll say, so 1.154 and using that value of omega 1.154, we then substitute that one for the magnitude. That will give us or if we'll use the x value. Okay, so remember that we have x is equal to, where is the value of x? There you go. It's 2 over 4 over plus omega squared. Okay. And so our x is, using that omega for 30 degrees, is 0.36. And our y, which is negative omega over 4 plus omega squared, will give us negative 0.21. Okay, and so we'll plot that one. Negative 0.36 and 0.21. So that's about right here. Point 36 and 0.21. Okay, and then we'll calculate now the tangent of 45 degrees, which is equal to 1 equals omega over 2, giving us an omega value of 2. And so the x component for that one, using this same equation, and omega equals 2, will give us a value of x of 1 over 4 or 0.25, and the y is negative 0.25. So we'll plot that one. 0.25, 0.25. So this is about right here. So that explains why I'm using this kind of scaling right here, so we could see properly. And then now for the tangent of 60 degrees, that will give us 1.73, and that is equal to omega over 2, and omega is equal to 3.46, giving us an x of 0.044 and a y of negative 0.076. 0.044 and 0.076, so that's about right here. And so if we'll connect now, we could now guess the shape, and so the shape will be kind of this half circle right here. So we could see that this is the phasor right here, that as the because this line represents your omega from 0 to infinity, and as it goes from 0 to infinity in this direction, the x value is decreasing and the y value is also decreasing. Does that make sense? And you could also see that in the Bode plot, that as your frequency is increasing, you will have that decreasing value of your magnitude, which is expressed in Bode plot in this way and expressed in the Nyquist plot in that way. But the Nyquist plot is just one plot that shows both the magnitude and the phase angle. So now if you calculate the omega from infinity back to 0, you will end up with the same shape but in the opposite direction. And so if you will try this command in MATLAB, Nyquist 1 over s plus 2, you will get that full shape. But we are only concerned about this first half from 0 to infinity. And so try to practice that one using different, g of s equals 1 over s plus 2 and s plus 4, and g of s equals 2 over s s plus 3, s plus 5. And see, you could also see how it goes with, check the shape of your Nyquist plot with the command from MATLAB. Okay, so this will be part of your final exam. All right, so good night for now, and sayonara from Japan.